Hello everyone, in this video we are going to cover a plate that starts out stationary and then suddenly starts moving at t greater than 0 with a velocity v sub 0. And then this fluid on top of this will take some velocity profile v sub x, which depends on y, which is our vertical coordinate, and t, which is our time. And to solve this, we need to solve this partial differential equation. dvx dt is equal to nu, that's not our velocity, that's our kinematic viscosity, nu, times d squared vx dy squared. So in order to solve this problem, we're going to make a few assumptions. So first, we're going to assume there's no pressure gradient and there's no gravity in the x direction. And we're also going to assume that we have laminar flow. First, let's figure out how do we get to this differential equation up here. And we can find that through the Navier-Stokes equation. So to solve this Navier-Stokes equation, we're going to use the fact that our velocity is going to be in the x direction, is going to be a function of y and t. We're going to have no y component and no z component of our velocity. And then we can go through this equation and cancel out the terms that aren't relevant and track down which terms are relevant. So we do have this term we're going to keep. We're going to get rid of this term. There's no x dependence on our velocity. We're going to cancel out these terms, cancel out our pressure, cancel out these terms, and save this one. So we're basically left with dvx dt times rho is equal to mu d squared vx dy squared. And we can move this density to the other side of the equation, and then we get dvx dt is equal to mu over rho d squared vx dy squared. And one shorthand for this quantity here is our kinematic viscosity, which has the symbol of nu. This is the Greek symbol nu. This is not velocity. That's important, otherwise this would become a very confusing equation. And we end up with this differential equation dvx dt is equal to mu, again not the velocity, times d squared vx dy squared. And our goal now is to solve this differential equation. To solve this, we need an initial condition, and that's because we have this time component. We need some initial condition to start us off. We need two boundary conditions because of the second derivative with respect to y. So as I just said, we need to think about the initial conditions. We need our boundary conditions. So first, for the initial condition, I'm going to jump back to that picture so we can visualize what's going on here. So our initial condition is what we know with respect to time. So we have this v sub x is equal to 0 at t equals 0. And then at t greater than 0, we have our no slip condition. This is actually going to be our boundary condition here for no slip. So jumping back here, we have at t equal to 0. And sometimes people will put this as t less than or equal to 0 because it's also true for before 0 as well. We have, for all y, our velocity in the x direction is equal to 0. So that's the starting point of this problem. The boundary conditions will be for t greater than 0. And the first one is for y is equal to 0. If we jump back to our picture, when y equals 0, we're at the bottom of this plate right here. And we're going to use a no slip boundary condition. So I'll write down no slip. Our velocity in the x direction is going to be equal to v sub 0. That's the velocity of our plate. And the other boundary condition we're going to use, we don't really have another length scale here. We don't have any other lengths that are relevant. So instead, we're going to look all the way up at infinity and say what's going on very far away from the plate. So we look at y is equal to infinity. We're going to say that our velocity in the x direction is equal to 0. This basically means that we're far enough away from the plate that the effects of the plate don't actually matter. So these are our conditions that we're going to use to try to solve this problem. Now, partial differential equations are tricky to solve. To solve this problem, we're going to first non-dimensionalize it, and then we're going to try to turn this into an ordinary differential equation, which should be easier to solve. So first, we can think about what are the natural length scales and velocity scales that we have in this problem. And so the main number that we have, if we look into what this problem statement looks like, is v0. That's some number, some velocity that this plate is moving at. So our first step can be to non-dimensionalize the velocity with respect to that velocity v0. So we're going to say, create a new variable phi, And this variable is going to equal to v sub x divided by v sub 0. So note the dimensions here will cancel out, so this is going to be dimensionless. So basically we can solve for v sub x and plug that into our differential equation up here. That'll give us v sub 0 times d phi dt is equal to nu. We have another v sub 0, d squared phi dy squared. And these v sub 0s will cancel out, so we basically have the same differential equation, except now we've replaced our v sub x with this dimensionless quantity phi. We can go back to our initial conditions and boundary conditions and try to write them in terms of this new variable phi. So if you remember our initial condition, I can jump back to that previous slide here, is that at t equals 0, for all y, our velocity is equal to 0. And we can directly rewrite that. For t equals 0, all y, and this time, phi is equal to 0. Since phi is just our velocity in the x direction, divided by v0. We have two other boundary conditions again, so that's both of these are t greater than 0. The first one was y equal to 0. This time we have phi is equal to 1. This is again our no-slip boundary condition, where our velocity is equal to v0. So that means that here our phi is going to be v0 divided by v0, which is 1. And then at y equals infinity, our velocity is equal to 0. So this time phi is also equal to 0. So we can rewrite our initial condition and boundary conditions in terms of this phi. And note that in all of these quantities here, we only have numbers. We don't have any variables. We don't have any values that depend on some dimension. We can hypothesize here as a way to simplify our equation, our differential equation, that all of these quantities, t, y, and nu, have some dimensionless quantity. And we can make a hypothesis here that our phi will actually only be a function of one variable, one dimensionless variable, which we're going to call eta. So this eta is going to be some dimensionless quantity that depends on t, y, and nu. So we have to figure out what is eta. If eta is equal to some function of t, y, and nu. So what is eta? Now eta is dimensionless. And our options are, it has to include y, t, and nu, again, our kinematic viscosity. So I'm going to write down what their units are, and we can try to figure out what eta should be. So y has units of length. It might be like meters or feet or inches. Time, t has units of time, so that could be seconds, it could be minutes or hours, but it's some unit of time. And our kinematic viscosity is again our viscosity divided by our density. And so if we work this out, that'll turn into length squared divided by time. Luckily here we only have two different dimensions. We have a length and we have a time, and we have these two quantities here. Y has a length, t has a time. So we should be able to put these all together and find some dimensionless quantity. So one way to figure out what eta could be is we can write down nu. Nu has units of length squared, so we have to divide this by y squared, and that'll cancel out our two lengths. And then we can multiply it by a time, because eta has a unit of time on its denominator. So this should be dimensionless. And that could be a value of eta. This is something that would satisfy the equations. We're actually going to flip this over and take the square root in terms of writing down eta. And this is just because people found that this gives a nice answer to the problem. This is what most textbooks will use when trying to solve this problem. So we're actually going to write down eta is equal to y divided by the square root of nu times t. And so this is still dimensionless. We're basically just taking this quantity we have written down over here, flipping it upside down, and then taking the square root. And we're going to make one more modification here just for convenience, and we're going to add a 2 here. Now that's kind of mysterious. I didn't like it when I first saw this, but this will make the eventual solution look a little bit nicer. People were only able to know that they should put a 2 here because they solved the problem out and then found that if there was a 2 in your definition for eta, that would actually make the problem look a little nicer. This is going to be our value for eta. And now we're going to make a hypothesis that we can write in our differential equation phi as a function of only one variable, eta. And then if we can write this out and we can eliminate the contributions from y and t, then we basically have an ordinary differential equation, which will hopefully be easier to solve than that partial differential equation. Here's where we've gotten so far. And again, our hypothesis is that our phi is going to be a function only of eta. So to find that out and to prove it, we need to figure out what is d phi dt, and later we'll figure out what is d squared phi dy squared in terms of eta. So we can use the chain rule here. We'll start with d phi dt. This is equal to d phi d eta. And again, we're changing this to a d because we're assuming or we're hoping that this is going to be only a function of eta times d eta dt. And now we just have to figure out what is d eta dt. So d eta dt is going to be, we're basically going to take the derivative with respect to t of eta, which is this quantity right here. So most of these terms will move out of the derivative. We don't have to worry about y. We don't have to worry about this 2 or the square root of nu. Our t is, we're taking t to the negative 1/2, so we can pull out a 1/2. So it's going to be minus 1/2. And then I'll add these two terms here, which represent the other terms that just come out of the derivative. And then now we'll take the last step of that derivative. It's going to be 1 over t to the 3/2. So that's our derivative. We can rewrite this a little bit. So first minus 1/2. And we're basically going to split up one of the square root of t here, and then 1 over t right here. And you'll notice that if we combine these two terms together, that's actually equal to eta, because we can move this square root of t underneath this square root. We end up with another term for eta, and that gives us minus 1/2 eta, and we can finish off by taking this t to the denominator right here, 1/2 eta over t. And so that's our d eta dt. We can put this all together. D phi dt then is going to be equal to d phi d eta times this quantity right here, minus 1/2 eta over t. Now we found this term, d phi dt. Next step is to find d squared phi dy squared. So first, let's just start with d phi dy. Again, similarly, we can use the chain rule. D phi d eta times d eta dy. And here now we have to figure out what is d eta dy. So we'll start with that, d eta dy. This one's a little easier. It's going to be equal to d dy of y over 2 times square root of nu t. And again, this denominator doesn't depend on y, so we can pull that out of the derivative. And derivative of y is just 1. So this is just equal to 1 over 2 square root of nu t. So we can rewrite this first derivative again as d phi dy is equal to d phi d eta times 1 over 2 root eta t. Now we can take the second derivative, and luckily we don't have to do a product rule here because this term right here does not depend on y. We just take the derivative of this term. So we'll end up with d squared phi d eta squared. And now since we're doing the chain rule again, we have to pull out another term, d eta dy, and then we have the same term from before. So just to be clear, this term here carries over right to here. That's this term on the right-hand side. And then this term here comes from the chain rule. So that comes out of this term. We've already solved for d eta dy, so that is just this quantity here. So we can rewrite this d squared phi d eta squared and then we can combine those two terms in the last step. So we end up with d squared phi dy squared is equal to d squared phi d eta squared times 1 over 4 nu t. And so that's our last term here. We can basically now take the d squared phi dy squared, plug that in to this equation right up here, and then we can take the d phi dt, which we found in the previous slide, and plug that in here, and then see what happens. Basically, we're hoping that all of these terms will cancel out, and we'll end up with a differential equation that just has phi and eta, and doesn't have any of these other variables t or y. I've written down the key results from the past few slides, and now we're basically just going to plug in this term here for that one, and we're going to plug in this term over here for the second derivative, and we're basically going to hope that all of our t's and y's cancel out, and we're just left with phi's and etas. So first, let's just write this down and see what happens. So d phi d eta times minus 1/2 eta over t equals nu d squared phi d eta squared 1 over 4 nu t. And already maybe you'll see that we can cancel some of these terms out. So first off, we can cancel these two nus. These two t's are on the same side of the equation. And we can also simplify a bit with this 4. So actually what we'll do is we're going to multiply both sides of the equation by 4. So we're going to cancel this out, and we're going to turn this 1/2 into a 2. And then we'll see what we end up with. So we end up with minus 2 d phi d eta times eta is equal to d squared phi d eta squared. And another thing often these differential equation books will do is rewrite all the terms on one side of the equation. So to finish up, we'll end up with d squared phi d eta squared plus 2 eta d phi d eta is equal to 0. And so far, our hypothesis seems to be working out just fine. We have right here just an equation with phi and eta. We don't have any y's or t's in this equation, so this looks good so far. And the last step we need to do to make sure this whole process worked is check the initial conditions and the boundary conditions for the problem. Here are the initial conditions and boundary conditions we had before for phi, t, and y. And now we're going to see what happens if we convert them into eta, which equals this quantity up here. Note that our differential equation right here only has is only a second order equation, so we can't satisfy 3 different independent conditions. So we will hopefully these will cancel out into something that looks a little bit nicer. So this term here, when t is equal to 0, note that our eta over here goes to infinity. So this initial condition turns into eta equals infinity, and we still have phi is equal to 0. Now our second condition here, when y is equal to 0, if we look up here, that means eta is equal to 0. And here we have phi is equal to 1. So far so good. When y is equal to infinity, if we look again up here, we have that our eta is equal to infinity. And again, our phi is equal to 0. 2 of these boundary conditions, this bottom one here and the top one, actually converged into the same boundary condition for our new differential equation. This is good. This means that we can write our differential equation like this, and we should be able to solve it and also satisfy everything that we knew before from our partial differential equation. We've put in all the prep work. Now we actually have to solve this differential equation. Now something you might know this from your ordinary differential equations class, or you might be able to check the back of the book for these solutions. In this case, we can take one step of this differential equation solving and rewrite this as our first derivative is equal to c1 times the exponential of minus eta squared. And so this is something that you just need to know. You can write it down and try to remember this if it comes up in the future. And then we can integrate this one more time, and we end up with phi is equal to c1 integral from 0 to eta exp of negative eta squared d eta, and I'm going to add a little bar here. This bar just indicates this is the variable inside of the integral. It is not the same as this variable up here, which is the bounds of the integration. And then we have an integration constant here. We're integrating from 0 to eta here because this is integrating from the moving plate, which is at y equals 0 and eta equals 0, up to a height and time defined by eta. We took the integral. We don't know what this integral is just yet, and in fact we can't actually evaluate this analytically, but we do have ways of figuring out what these values are. So again, we can think back to our boundary conditions. If I jump back to the previous slide, one of our boundary conditions is that when eta is equal to 0, our phi is equal to 1. So let's try to plug that in here. So phi of eta equals 0 is equal to 1, and that's equal to c1 integral from 0 to 0. So whatever this is, it's going to be equal to 0, plus c2. So this all goes to 0, and we end up with c2 is equal to 1. Now that we know c2 is equal to 1, we can use our last boundary condition to try to solve for c1. So we get phi is equal to 0, c1 integral from 0 to infinity of this term exp negative eta squared d eta plus 1. And so we can solve this for c1. So c1 is going to be equal to negative 1 divided by this big integral expression. Now luckily this integral, even though it goes from 0 to infinity, this is a known integral. This is actually very similar to a normal distribution, if you're familiar with that. So if you're familiar with probability theory, you may know this integral. And this integral right here evaluates to the square root of pi over 2. So we can solve for c1 if this denominator is the square root of pi over 2. c1 is equal to negative 2 over square root of pi. Finally, we can plug these values in, c1 and c2, and solve for our final expression for phi. Here's our solution for phi as a function of eta. Now we can't solve this integral analytically, but it turns out this is an important integral in probability theory, so a lot of people are interested in solving this. And if you combine this prefactor here, this is actually a well-known function called the error function. So we can actually rewrite this phi in terms of the error function of eta. And so here's a simpler way of looking at the same math. This is within this error function is this exact expression. So we haven't changed any math here. But what you can do is you can go into certain computational functions, like you can use Python or MATLAB. I think even Excel has an error function feature. And then you can use that to solve for your phi. And in addition, we can rewrite this a little differently as well in terms of the complementary error function if you want to get rid of that 1 minus term here. The complementary error function is basically just defined as 1 minus the error function. And so here are a few very compact ways of writing this, and if you wanted to compute this, you could figure this out. Now, since in this whole process we've turned these into non-dimensional quantities, so if we wanted to calculate something, it would be good to actually turn these into their real dimensional counterparts too. So if you remember, our phi is equal to v sub x divided by v sub 0. So here now we can actually calculate the velocity in the x direction. And that's equal to our complementary error function. If you remember, our eta is equal to y divided by 2 square root nu times t. And so now you could plug in some value for y, some value for t, a value for the kinematic viscosity, and then figure out what your velocity v sub x is, just using this error function. So just to give you a rough sketch of what this looks like, if we plot on the vertical axis v sub x over v sub 0, remember this is also just phi as another way of looking at it, and on the horizontal axis we can plot eta is equal to y over 2 root nu t. The function ends up looking something like this, where here's 1, 0. What's interesting about this is that as you change the different parameters. For instance, as you change time and you increase time, the overall shape of the function will be very similar. And similarly, if you change the distance away from that plate you are, and then you change time, all of these functions are going to have a similar downward sloping curve. And that's why our method worked here, where we were able to combine all of these quantities together here into one variable eta. Whether you change time and hold y constant, or change y and hold the time constant, the overall shape of the curve will always look the same. I hope you enjoyed this video. Thanks for watching.